Final talk of the morning is by Edgar Costa, and he's going to speak to us on counting points on smooth plane quartics.
Thank you for the introduction. Okay, so I'm here today to talk about counting points, very similar to what Elsen just did. Let me just jump to the problem immediately. I don't want to spend too much time in introductions. So my goal today is about computing the number of points of a smooth plane quartic. And why do I care about these? Because I want to basically compute L functions. And so what's an L function? If X is a smooth projected curve, then I can write my level L function like this, where my denominators are just basically the numerators of the theta function, where that lovely polynomial is agreed to G, and it has a special shape. So what I'm really trying to do is compute the first coefficient. And I could spend like 5 minutes telling you like why we care about these. I put some keywords here, but my goal today is really compute the number of points as fast as I can. So to be clear, when you expand your denominator of your, or when you expand your numerator of zeta function, which is the denominator of the Euler factors, you get the first guy is the AP, and that's exactly what I want, because if I want to compute all the n's up some bound, for example, I need to do that if I want to compute the L function, or if to be the zeros of the L function, I kind of need to go up square root of the conductor of my curve. So, and to do that, I really need to compute basically all the APs to the E. And really, if you think about it for a bit, you can spend all the time that you want on the higher powers, because all the time you spend is really on just the APs. So that's really what I want. I want to a fast way to compute APs. I'm okay to spend a couple of hours on the other ones, because there are very few of them. So the cost of doing this is fully limited by compute APs, and we know how to do this already in a reasonable amount of time. So what I say, like in this case, say computing all the APs up to n. So I really can't see my own pointer, and it's about average polynomial time per prime. So obviously, we're going to do these periodic curves. Indeed, that's not even average polynomial time. That's polynomial time for each prime. But then, if you ask for higher cyclic covers of P1, there's a series of algorithms, mostly all of them more or less based on the same idea. For apolytic, we have the original paper of David Harvey saying how to do this for apolytic curves. Then you have improvements of Harvey Sutherland. Then you also have other improvements for geometric apolytic curves. And finally, for superlative curves, basically when you take m bigger than 2, you have Sutherland doing also that. And all these work exactly the same way. They do it by trying to compute some exact coefficients of f to the x to some power of order of p. It's very similar to what Elsen was just doing right here. Elsen showed you that you need to compute one coefficient. For these curves, you need to compute g-squared coefficients. And just want to show you that this is really like ants kind of thing, because there are ants everywhere. I'm quite sad. I was doing something else 2018, so I didn't touch this at all. So I could put a sequence there, but it's live. And today, so we're gonna switch a bit gears, because so far we've been doing like univariate. We reduced the problem to univariate problem by looking at the cyclic covers, and now we're going to do the next thing, which is smooth plane quartics, which require now 2 variables at least. More ants. Yeah, the goal, by the way, is to beat David Harvey in 2018. He had a bunch of ants on his slides, and I'm going like, who has more ants? I win. Okay, so what are smooth plane quartics? Smooth plane quartics basically just given by a quartic equation and some smooth assumptions. I'm going to call that forever f, and f is, I'm going to think about this as phi over z, and we'll take degree of f equals 4. And we'll present 3 algorithms to do this, but in the end of the day, I'm really like lying to you a bit. I don't not only compute points, I'm going to compute the Cartesian matrix, and then take the trace of that, which is trace of Frobenius, and that's enough for p large enough to get my number of points. And obviously, because I'm trying to do this for all the primes up to some bound n, I don't care about small primes. I don't care about the primes where things go bad. So basically, I'm saying like for p large enough, this is good enough, because for p large enough, model P, it beats that. And so here's the lovely Cartesian matrix. And it's a complicated formula. I don't want you to look at it. I wanted to visualize it with more ants. So I picked P equals 7. So the idea is that, and basically the goal talks about pictures. And if you go out of this talk with a picture in mind and a bit of ants, it's fine, because that's really the goal. So the point is that these 9 coefficients, so because now I'm genus free, are basically these 9 points, and they're kind of spaced out P apart. So basically, if you think P equals 1,000,000, now we'll have this triangle size of 1,000,000, and you want it to go to the kind of almost middle coefficients, not really in the middle, and get those only. And obviously, we could compute all of them at the same time. So that will be like Math's algorithm about OP squared, which would be very expensive. But we want to basically just go there like a surgeon and like pick those guys and walk away without spending much time. So that's what we're going to show you today. So maybe I should give you a crash course on these kind of ideas of average polynomial time with the Riemann trees. So they all work the same way. You find some recurrence, and then you realize your recurrence works not only model P, but over Z. That makes sense when you make model P. So basically trying to compute a bunch of partial products, M0 to Mn minus 1, over some comprime integers, M0 to Mn minus 1. You should think basically these guys are like, they're all ones, and once in a while they're primes. You know, when MP is prime and everything else is 1. And in our case, that I'm going to show you, we can now do these with R by R matrices. And in that case, the cost, surprisingly, is not RQ or R omega, but R squared. Because what's happening here is that we're multiplying really matrices of large integers. So the cost is not really the matrix multiplication. The cost is really like the FFTs when you're trying to multiply these numbers. And basically, you start with the matrices, you do FFTs, you get your FFTs, and then you multiply them. So in the end of the day, it's just R squared, not R2 or R omega. But overall, so our cost is R squared n log cube of n, and the space is also about the same, but now it's just log n. If I wanted to save that log n factor, I could, instead of this called Riemann tree, I could call it Riemann forest. More complicated algorithm, but the idea is the same. Instead of doing all in one go, we do batches. So our goal here is really to try to get R as small as possible. As you know, if you notice, when I was talking, one question of Drew was, what objects are your matrices? Because if they're like 100 by 100, great, the algorithm is great, but it's not going to go very far. But 9 by 9, that's tempting. That's why Alcens can run this algorithm like in a couple of hours in his laptop. So I want to make R small, but I should be careful because making R small has side effects. Because I'll explain more the side effects later on, but the idea is that sometimes it's better to have a matrix that's more sparse, which is larger, with small coefficient, and multiplying very small matrices with very, very large coefficients. Because in the end of the day, FFT is what's beating you when you're running these computations. So I'm going to present 3 possibilities where R is going to be 66, 28, and 16. So the first one is not even new. We call it optimize Harvey, because this comes from the Davis paper, Computational function for arithmetic schemes. And again, the idea is like we want those coefficients, those 9 coefficients, and if you look at this paper and you manage to go through all that lovely notation, you realize that it gives you a matrix, Mi, over the integers, 66 by 66, which has a lovely property. And I explain here how you get the matrix, but that tells you how to go get these coefficients on some, like, you should think about that like some region on that triangle, how to go from those coefficients to these coefficients. So you think about that, in the end of the day, if you make I equals P, that's what you get. So you go from something that you understand very well. So G is my auxiliary polynomial. We know how to take the power of P to that, very easy, because we all know, like, very easy model P, to be precise about that. So it allows us to go from G to the P minus 1 of that thing to F to the P minus 1 of that thing on one special region. And so the 66 we need comes directly from David's paper, what we realized that if you really want to compute the Cartesian matrix, you don't really need like the whole thing. You just need 3 rows of that 66. So for example, instead of computing the whole product, we can just compute almost like a 3 factors time. Oh, there's a typo, M0 twice. You basically compute 3 factors times the partial products, and that really saves a lot of time. So I'm not going to elaborate much on this one, these old things, but should think about that if you had to save humanity tomorrow and you had to implement an algorithm by tomorrow, I bet all of you could do this in like 1 hour or less. This notation is hard, but that's the simplest one because you just need to write one thing, one matrix. But you don't need to do that. Our code is public, or at least our prototype code is public in CodeCalc, so we can just look at it and save humanity. Okay, so I'm moving past this because now I'm talking about the other 2 algorithms, which are somewhat new, even though they've been around since 2014. It's been a long battle for this paper. And the idea is very simple, that as the previous algorithms for like cyclic covers, what you realize that your coefficients of f to the p minus 1 in this case are not something random. They have some relations. So indeed, here I just use f to the m. Sorry. And the f to the m solves this like lovely differential equation of polynomials, whatever that means. So what I'm saying is that if you pick f to the m in place f to m instead of g, you get an equality. I hope you agree with that. I'm not going to try to find what this means at the differential equation. And where here my di is just like my preserving degree derivatives. And now you can ask yourself like, okay, these are polynomials. So I can look at one coefficient of those. So I can look at the coefficient of x to the w, and then I get some lovely linear equation. Or like, indeed, I get three equations. And the first one is that they're not 3 equations, they're only 2. Because if you use other identities, and you add them together, you get something trivial. You get 0 equals 0, something like that. So indeed, you only get 2 equations. But this is what we're going to use. That's as simple as that. We're going to use this to basically get exactly the coefficient we want. So more ends. So the idea, now visualizing, ignoring the equations, we don't care about the equation anymore. If you look at the case d equals 4 and m equals 4 in this case, then those equations involve this triangle with the ends. And the idea is like, okay, maybe I can combine, make the triangle bigger and involve more equations. So one way is like, I can just expand the triangle, like, okay, how many equations are now spanned, or I can cover this triangle with. And the reality that in this case, if I want to move, for example, if I would like to move the triangle to the like is hard, right? Yes. Yes. If I want to move the triangle to the right, I could realize that I can put 4 relations here. So, which are these triangles here. And now if you count along the line, how many unknowns do you have? Supposedly you have 8 unknowns. So, 2 times 4 is 8. And I have 4 equations, 4 unknowns. So if life is good, you can solve it. And that's what I'm claiming you can do. You can just figure out how to fill out those. So basically, this is the whole idea of algorithm. So you just basically combine enough relations in a way that it can allow you to move around. So obviously now I can go either right or to the bottom, because if I want, I can simply forget. If I forget about this guy, then I have another triangle which is of the same shape or at the same height, or I can go downwards by forgetting the guys at the top. So maybe to visualize it, I put a big triangle. So what's happening here is that I know the ends, and I want to move my triangle to the right. So I can just fill up the whole triangle, forget what I don't care about anymore, and just maybe able to my triangle to the right. Now, if you count the number of ends, you're going to count 28. So you can imagine how many ends I already have in my slides. But the idea is that you basically get the 28 by 28 matrix to do this operation. Now, this should not work for everything, so I shall tell you what are my assumptions. And me be able to move to the right, I need to assume some non-degeneracy conditions about my curve or about my f. So the first one is basically saying that my curve does pass through the 3 points 1, 0, 0, 0, 1, 0, and 0, 0, 1. And the other assumption is that my x intersects my hyperplane axis transversely. So these are totally assumptions depending on the model. So these are very mild assumptions. Indeed, for large P, if you give me a curve that does not specify these, I can do a random change of variables, and most likely on the first try, I'm going to get a new model that satisfies conditions. And obviously, changing the model does not change either the trace. Sorry, it doesn't change the AP, so the trace of Frobenius or the normal points. So here's the new algorithm. We start a triangle because we can compute these coefficients very fast, all of the corners, right? Because you know it's just doing f to the p. So the only coefficient involved here is like you just need the coefficient of the x to the 4, so x0 to the 4, and then you get that guy and you can walk. Then you walk along the edge, just following the ends. That's very cheap because that basically we're back down to the case of dimension 1. Indeed, here we can do polynomial time per p, and then finally you walk inside. And then once you walk inside, you get to those blue dots, and so I'm working at fp minus 2, and from that square I can then get the coefficient I want of fp minus 1. So maybe just to say that clearly, so walking along the edge takes polynomial time. It's basically a powering of a matrix p times. We all know how to do this easy, but the hard part on this algorithm is to walk inside. And here I claim I can do it with one single remainder tree or remainder forest. And the idea is like something magical going on. That first is that the matrix that take me from this red dot to this blue dot, and from this red dot to this blue dot are exactly the same. So there I can already say, instead of having 2 remainder trees there, I only have 1. Even more magical is that walking from here to here is the inverse of walking from here to here. So once I have the matrix, the 28 by 28 matrix that takes me from one of the red dots to one of the blue dots, I can get all the other ones. So that's why I only get 1 remainder tree. And obviously, we all care about constant factors. So your salary could be 3 times higher. We'll take it. So here's the thing: like we really want that saving factor of 3, and that's what we get. Questions? This is the most important picture of today. Okay, moving along. Okay, but I've not yet told you how I get 16 by 16. I don't really have time for that. That's also a big part of the paper, but I'm going to give you the idea. The idea is that if you just do some numerical computations and you make these 28 by 20 matrices and you look at them, you realize that the rank of these matrices is always 16. If you also assume smoothness, which is I've not assumed smoothness so far, even though I was computing the Cartesian matrix. And what we realize that all these triangles, they are like those equations I gave you initially, they're cutting down a 16-dimensional space of all of that 28-dimensional space. And there's all like triangles are all compatible, and all the vector spaces are compatible. So what's happening really is that you just don't need to work in 28 by 28. You can just work on a smaller vector space. On one hand, doing these costs makes our coefficient increase, but we can amortize that because basically the way you move is basically compress, decompress, compress, decompress. And every time we do these steps, we can extract a common factor, which makes our matrix smaller again. And in the end of the day, we really get a speed up of 3, which is somewhat surprising that we can do the constant compressing without any real cost. And as we are at ends, here are the lovely running times. So here we're comparing the average polynomial time versions. So here's the simplest version possible, which is optimized version of what David wrote in 2015. And then here's the 28 by 20 version, and then the 16 by 16 version. And the key part is that you can look at the fact that it can't really behave as you expect. It's really like you get really constant, like if you think about the constant was R square, really the savings are more or less like what you expect for R square. David, you're confused.
I'm confused because at the bottom of your table it looks like the 28 by 28 is better than 16 by 16. Is there a scaling factor or something? 20.3 seconds, 28 seconds.
Milliseconds behind by the number of lines up to that.
Sorry?
Here's a typo.
The seconds column in the 28 by 28 is incorrect. I can tell you the bottom.
There's a
The bottom row at 2 to 23 would be 11,400.
There's a typo. I'll save it. Don't worry. Where the papers? It was copy pasted. That's the lovely part about this.
My table 2.
But it's so hard.
It's the bottom table on that page.
Okay, sorry, that's the lovely table I was trying to put on slides. Oh, I see. Indexing. I erased the column I was not supposed to erase. But thank you for
Oh, I
having.
see.
Yeah, there was the.
I was going to ask you if the ants represented bugs in the code.
Oh, for sure. There are plenty of bugs in the code. I don't know any of them, but if you find them, let me know. Okay, so that's the point here is that maybe it's easier to look at milliseconds per prime, and you can see that the factors grows as you expected if you do the math of like 28 by 16 squared, 66 by 28 squared, and so on. Okay, and next one. Hopefully, I don't mess up that one. Yeah, this one. Okay, sorry. I'm going to ignore light. And I just realized my code. There are bugs in my code right on the table, so I cleared it. And so now we can compare all of the other versions which are not like which are not average spawn time, because there are the competing algorithms which I didn't bother to spend time on it. I also don't want to take your lunch away. And obviously we can also implement the skirt of the baby step, giant step version. But what I want you guys to notice that each one of us had a version about which was linear. We can look at the Harvey implementation, P log P. You can look at Costa's implementation, P log P. You can look at small jack, which is also basically true. And the key part here is that basically Sutherland plus Costa plus Harvey are much better together because any of these algorithms beat all the others before. So that's the point we want to make. And because I'm really afraid of more typos, I'm just going to use the paper to show you the rest. And if you might wonder about like, oh, what happens in like, if you compare to other genus free curves, because I just basically, we took care of the generic case, but you were like, oh, but I really don't care about smooth plane chords. I care about this particular case of like genus free curves. And here's all the average polynomial time algorithms we have. By the way, all the way it takes to Drew to implement. So like, they have more or less have some optimization. You can just compare that. Yes, dealing with the generic case is a bit more expensive, but surprisingly, not much more expensive than the geometrically hyperelliptic. And so I end up here, and I hope you go for lunch.